Right. All right. Good day, ladies and gentlemen. Welcome to the Saab-NTU Joint Lab as well as Purdue University webinar on underwater robots, trends and challenges. I would like to have a few administrative reminders for the attendees. We will have this webinar co-chaired by both Assistant Professor Liu from Purdue University and Associate Professor Chai from NTU, Nanyang Technological University in Singapore. We are managing 3 time zones here, or maybe even global time zones, US, Sweden, and Singapore. So good morning, good afternoon, and good evening to everyone. We would like to remind the attendees, if you had questions for the panelists, to please use the Q&A function and type in your questions, and the co-chairs will moderate these questions. Unfortunately, you will not be unmuted, and you can only type in your Q&As. If at any point in time the co-chairs do have interest to have more discussions, they will most likely invite folks to unmute, but by default we will not be doing that in this webinar. This webinar is being recorded just for everyone's information. I will hand over the floor now to our co-chairs, Prof. Chai and Prof. Liu. Thank you. Go ahead,
Right,
Prof. Liu. Yes.
Good morning, good afternoon, and good evening, everyone. This is Chen Cheng Lu from Purdue. I'm honored to be co-chair with Dr. Chai to co-host this first webinar. I'm going to introduce our Director of Globalization of our college at Purdue University, Ms. Elizabeth Barajas, to give us the welcome message. Thank you very much, Elizabeth.
Thank you, Professor Liu. Hello, my name is Elizabeth Barajas, and I'm the Director of Globalization at Purdue Polytechnic Institute here at Purdue University in West Lafayette, Indiana, USA. On behalf of all of Purdue University, I wish to welcome you to today's live webinar on the topic of underwater robots, trends and challenges. Today, we bring together experts from opposite parts of the globe for an accessible academic presentation and lively discussion. International collaborations like this are crucial to the growth, sustainability, and diversity of higher education. And we're happy to be here today, collaborating with our colleagues at NTU and Saab. Today, we are navigating that 13-hour time difference, and we thank you for joining us either this morning, this afternoon, or this evening. So if you're viewing this from Singapore, apologies if we continue to say good morning. And without further ado, it's my pleasure to introduce Professor Wee Kim Tao Chair of NTU's School of Mechanical and Aerospace Engineering.
Thank you very much, Elizabeth. I'm going to give the floor to Dr. Chai.
Hello, good morning, good afternoon, good evenings. Okay, it's my pleasure to introduce Professor Wee Kin Hiao, Chair of the School of Mechanical Aerospace Engineering. He's also the Chair of the Working Committee for the Saab-NTU Joint Lab. Prof. Wee, please. You're muted.
Sorry, I need to unmute myself. Thank you very much, Prof. Chai and all guests. A good day to everyone. It is my great pleasure to welcome you to this first webinar with Saab-NTU Joint Lab and Purdue University. I would like to thank the organizing committee, particularly the two co-chairs, Dr. Lee and Dr. Chai. We are fortunate to have the support of speakers from Purdue University, Saab and NTU Singapore. Who will present their work in relation to underwater robots. I'm sure you will find this session fruitful. Let me give a short introduction to my school, School of Mechanical and Aerospace Engineering. We are one of the three pioneering schools of Nanyang Technological University, which was formed in 1981. Today, we are probably one of the largest mechanical engineering schools in the world and attracts the best minds all over the world to contribute their expertise and ideas to our local education and research. We work closely with industry and host numerous corporate labs in collaboration with MNCs such as HP and Rolls-Royce. In 2018, we partnered Saab to establish the Saab-NTU Joint Lab to forge a long-term partnership in research in air traffic management and underwater robot. Purdue University is not alien to us, but Purdue University has been one of our partners in global mobility and exchange. In NTU, about 75% of our students involved in one way or another, different form of global mobility and exchange programs. In 2019, I just checked a few. So we have 4 undergraduate students from School of Mechanical actually visiting Purdue to carry out their one semester studies to pursue courses and research. And this has significantly reduced over the last 2 years because of the pandemic. So in this semester, I was told that we have 2 students visiting Purdue University. Personally, I visited Purdue University once every 2 years to attend the Compressor Technology Conference. And that was since 1992. That was my first conference in Purdue. It was then chaired by, I think, Professor Raymond Cohen, and who has seen retired. Now it is taken care by the Professor Eckhart Grohl. Just last year, I gave a virtual keynote in his invitation in this conference, but delayed for about a year. So this webinar brings together like-minded researchers, and I sincerely hope that it will pave the way for potential collaborations. I thank you for your participation and join the conference. Thank you.
Thank you, Prof. Wee.
Thank you.
Thank you very much, Dr. Wee. I am going to introduce my dean, Dr. Terry Berger, to give us an opening speech. The topic is value of collaboration between Purdue University and NTU. Dr. Berger.
Thank you, Professor Liu. So I want to start off by offering my sincere gratitude to Professor Liu and Professor Chai for initiating this collaborative webinar. And developing new collaborations, especially international collaborations, is not an easy task, and it requires commitment and drive from both sides. I know we would not be here today without the commitment of our colleagues, and I say thank you. I'm also grateful to be able to listen in on this webinar and to hear about the great research that's happening at the direction of our respective faculty. Excuse me. As you can probably guess, I'm fairly familiar with the work of my Purdue colleagues, but even so, I still appreciate hearing about their research with an eye towards collaboration and how research with and about underwater robots is an area ripe for development, and I sense a lot of opportunity coming from the discussions this morning. I truly believe that our research will have the greatest impact by working with others from different backgrounds and from complementary areas of research. And a partnership between Purdue and Nanyang Technological University, which also leverages our respective relationship with Saab, is simply a smart thing to do, as it will provide opportunity to elevate the research happening in our respective institutions to a new international level. And such international partnerships have a huge positive impact on students and help to shape the workforce of tomorrow. These kinds of international collaborations are very important to Purdue and crucial to addressing global grand challenges. We are grateful for the opportunity and look forward to next steps in this collaboration. I'm confident it will lead to some very impactful work. As we move forward, I think the right approach is to get some early wins as success leads to greater success. It's important that we take time and prioritize getting to know each other, building trust and forming strong relationships. And webinars such as this are a great first step to start building a strong foundation that will allow for successful collaborations in the future. I look forward to seeing how this develops and doing what I can to support the collaboration between our two institutions. Thank you for letting me join today.
Thank you very much, Dr. Berger. I would like to introduce Dr. Chai to continue our next section, which is our exploratory discussion among two universities. Thank you very much, Dr. Chai.
Thank you. Thank you, Pablo. Today, actually, we have a number of colleagues joining us, either from the Saab-NTU Joint Lab or from the school. But my boss is here, Prof. Wee, representing us about 100 plus staff from MAE. So let's hear from two sides, see how we can develop kinds of synergy in terms of research collaboration, in terms of student exchange, right? Okay, very importantly, we have Dr. Juvis N is research director of Saab Singapore, and also the co-director of this Saab-NTU Joint Lab. She's here, and let's talk to you what will be the area of common interest.
Sure, thanks, E. I would not be the one leading this conversation, so I guess all of us can freely communicate. So I would like to invite the two main coordinators to start the conversation, and then the rest can probably just join in and contribute. Importantly, I have my colleague from Saab joining us from Sweden, Jan, who is very experienced in this area of research and is very well exposed to the research environment in Europe. So please take his input very seriously. I'm afraid to say this is not my area of research, and I'm not an expert in this, but I do find this extremely interesting. So that's it today, and please go ahead with the discussion. Thank you.
It looks like we have Professor Mahmoodian Nina here with us, and Dr. Voice and Dr. Ming will join us later on. And Nina, would you please introduce yourself quickly and about your research areas and research interest with NTU? Thank you.
Yes, thank you very much. I'm Nina Mahmoodian. I'm Associate Professor of Mechanical Engineering I work on persistent operation of mobile robots in challenging environments, and what more challenging environment than water. Today I will talk about our focus on persistent long-term operation at sea with multiple applications for physical oceanography, Arctic observation, coastal surveillance, and our recent progress toward achieving a robust autonomy at sea. And I'm very happy. I see a lot of potential in this collaboration with NTU, and looking forward to hear from others and also find new opportunities for collaboration.
Thank you very much. I have known Dr. Richard Voice for many years, and I remember that he studied with robotic system and also autonomous system, and he is leading an important lab here as well. And it's a kind of interdisciplinary lab with different universities, also different colleges here at Purdue. And Richard will deliver later on about his current research projects related to underwater robotics and related to agricultural activities. And we have Professor B.C. Ming is going to talk about underwater, using underwater robots to collect samples for environmental impacts and for other possible applications. And again, that would, our side, since around like November, right, Dr. Chai, we were talking about having this seminar, and I try to test water, what both sides can do, how we can exchange faculty and students, how we can join together to draft grant proposals and finding fundings for both universities or research associates or professors. Do you have any comments right now? Or the question might go to Professor Diao as well. And I think that we are all very, very eager to know about the next step, but of course that we can talk about that later. But it looks like we don't have a lot of time today, only 2.5 hours only. And so we use these 5 or 10 minutes only to briefly know each other and also want to know about the next step. How do we move forward?
I think I would just chip in and say something, because I will have to leave around 9 p.m. Still have to go and fetch my daughter, who is taking some night classes in NTU. So sorry about that. I think it is I mean, this is the first session. I think this session will be extremely useful, as what Dr. Burgett to say, that we get to know each other, forge a relationship, and then eventually we can talk more details among professors with a similar expertise, and how we can actually expand this from research, faculty exchange, even to student exchange. I believe whatever we are going to do, it will definitely benefit Purdue or benefit Singapore as well. So, you know, Purdue University has a very established and very well-known mechanical program. You do a lot of good works, you know, a lot of wonderful works in, I mean, to me, I mean, Purdue University is the best university in compressor engineering research, you know, since early 1960 plus, you know. So when Tecumseh donated the first laboratory to Purdue University, and since then it has become one of the best research institute in this area in the world. And Professor Eckhart Grohl, I know him quite well. You know, now I keep seeing him moving up the ladder, the career ladder, and he's still very young. So when he started joining the Purdue and all these things, so we get to know him, and now we are friends. We always meet in most of the conferences. So I would say that get to know each other, find out similar area that both of us are interested in, anything that benefit to both sides. I think we should go ahead and do it. You know, we should probably increase student exchange program, should make it even have more students coming both sides. Purdue University campus is very nice. Big campus, and I always been there. Sometime in July, it was quite warm, but then, you know, in general it is very nice. So I mean, the whole Purdue town itself is a university town, you know. So and I remember last time we used to use a textbook written by our heat transfer textbook, written by professors from Purdue University. So I think the relationship with Purdue should be, the foundation has been already very strong, but moving forward, we want to do more research-based collaboration. So if you look at the two mechanical engineering department, and maybe later on we should extend it to entire university, to probably global office and international office that we also have. So I think we can link this up. And I think in mechanical engineering school in Singapore, we pride ourselves to be a very strong mechanical engineering school, you know. So even though we are relatively young as compared to Purdue University, but I think compared to the Polytechnic Purdue, probably we are, you know, you started in 1964, so we are 1981, so we are still much younger. So we are very young, but we work hard because and we have a very, very big school. You know, we have about 100 professors and 3,000 over students, undergraduate students. So if you include master and PhD, probably we have 500 PhD students and another few hundred more master students. So I think that there's a lot of collaboration we can do, and I hope that we can take this opportunity to know each other better and to actually move forward. I mean, not just by having this webinar exchange idea, but we have a really close collaboration, you know, really do something 2 + 2 = 3 or 4, that kind of situation. Thank you very much. So I think with that, I probably have to leave and then go and pick up my daughter. I'm sorry about that. So I wish the conference a great success. I'm sure it will be. Thank you, and bye-bye.
Thank you, Dr. Tiao.
Thank you. Bye-bye.
I remember that, of course, that NTU is a very, very strong, probably the strongest engineering university in the whole Asia area, and very with a lot of good programs there. And Purdue also, we provide from air to ground to underwater, of course, to space. We have a lot of research projects related to it. My departments, we are in more on civil aviation side. We work on the airports and also traffic management system. And that I work with our friends before in China in UAVs and air mobility system in Shenzhen and Huizhou area. And so we do have some experience. That's how I got to know Dr. Chai in China when we met there in 2018 in a conference, and start to know each other, knowing about NTU, knowing about Purdue likewise. And then we do have a lot of same pedagogical areas, degrees or research programs. They are very, very similar and close. So I strongly believe that we will have very, very good output regarding collaborations, student, faculty, research, and everything that we believe that could be very, very helpful to our students and faculty, and also our communities as well. Dr. Chai, you want to say something?
Thank you very much, Dr. Luz. We have Professor Menkun here. He is associate chair, take care of research in the School of Mechanical Engineering. Prof. Menkun is now a panelist, I think. Perhaps he will visit. Hi, Prof. Menkun.
Hi. Okay. Yeah. So sorry for that. I've been fighting with my computer to get connected. End up I can only connect through my phone. So I think most of the things I want to say are already covered by our chair. So from NTU point of view, we are definitely very happy and very interested in exploring research with Purdue. So we are seeing this underwater robots as a starting point, and we wish to extend our collaboration to many different areas through different models like student exchange and visit or research attachment and joint proposal, joint funding, application, so on. So yeah, I'm definitely very happy to see what has been developed, and very happy to see the future development from this collaboration. So thank you.
Professor Chai, Professor Liu, I would really just like to step in and echo a little bit of what Professor Wee said. And he mentioned that we're here today to talk about research collaborations, but activity breeds activity. And I'm very excited about how faculty to faculty research collaborations like this webinar can lead to more exposure for our universities to our student populations. And while we've seen too, for a handful of students go back and forth, the more our faculty work together, the more our students are going to want to work together. And that's something that will benefit them in their future careers. As we're here today, spanning all of these time zones with people from all over the world viewing and participating, those are skills that our students will benefit from. So I thank all of our panelists today as you set an example for our students and help us spur those curious minds.
Thank you, Elizabeth. That's great comments to everyone, encouraging too. Well, let's move on to our first presentation. The first presentation will be.
Sorry to interrupt, Dr. Liu. Maybe we could invite as well one of our Saab colleagues, Jan. Maybe you could highlight what you think might be beneficial from Purdue and NTU as well from the perspective of Saab. Yeah.
Yes, of course. I'm sorry.
Okay,
Go ahead,
yes.
Dr. Yang.
Yeah, just like I said, really good to be here. See you all, and yeah, I think this could be a really interesting opportunity, because what I'm sort of thinking, looking at the coming presentations and what you have been saying is quite interesting from my point of view, because I've been to quite a few of similar conferences about underwater robots, autonomy, blah, blah, blah. And it often focuses very much on autonomy, software, and that sort of thing. And what I see here and hope is that you're also focused on actually getting things, how to say, the physical things, mechanical engineering, how these things actually survive in this harsh environment. And because at the end of the day, these things may be as smart as humans moving forward, but if they are not reliable and they work in the real world, it's not going to work anyway. So yeah, I'm looking forward to this.
Thank you, Jan. And once again, I'm very happy to let Saab-NTU Joint Lab host this event, and thank you all for participating. We're very proud to be working with NTU and very proud to have this extended collaboration with Purdue. And I hope the rest of you will enjoy this webinar as much as I will do. Thank you.
Thank you, Liz. Thank you. Okay, Dr. Liu, now let's move to the next portions for the technical presentation.
According to the agenda, our first presentation will be from Dr. Richard Voice. Richard, are you here?
I believe he's having some issues logging on. So perhaps we could skip ahead if that's okay.
Yes, of course. Dr. Chai, you want to introduce Professor Sheet to us?
Okay, sure. Speaker from NTU for this first talk, we have two persons. Professor C, he's joined since when always doing robotics. He was a former director of NTU's robotics centers, and also HOD of Robotics Mechatronics divisions. Today is going to share with us more on the collaborative kinds of robot. And we have Dr. Hui will do the second part of the speech, talking very much on underwater robotics applications. Okay, Prof. C, please. You're muted. Please unmute.
Okay, can you see my screen?
Yes.
Yes.
All right, what I want to show today is this, that in underwater, the ROV pilot has a lot of duties and tasks which he needs to optimize. He needs to worry about the low-level tasks, or possibly if you are dealing with ship hull cleaning, to make sure that all the barnacles are removed. He needs to worry about the fact that the sweep from one pass to another overlaps sufficiently so that the removal of materials is effective. So what I'm trying to share with this is that there's a lot of tasks that the pilot is responsible for, and this normally places a very high cognitive load on the pilot. As we progress outside of the underwater environment, we find that the robots are becoming more and more intelligent. And in such scenarios, we tend to give the robot more responsibility to assist the human operator in the task. Yeah. So what I'm suggesting is this.
Can you hear us? Maybe before you proceed, your slides are not on full screen, so we are seeing a very blurry version of the slides. So if you could just do a full screen mode of it, that might help. Yes.
Is this better?
That's better, yes, but it's not on full screen. If you could just maybe click the slideshow, that would be good. Yeah, thank you.
Is it this?
We're seeing the PowerPoint, but not the slideshow. There's a button just beside the minus sign. Yeah, okay, now we see it on full screen. Thank you, Prof. C.
Okay, great. Thanks very much for the prompt. Yeah. What I'm trying to share is basically this, that I'm attempting to address the excessive cognitive loads on the ROV pilot by recognizing that the ROVs now are becoming more intelligent, and they can take on greater responsibility for the lower level tasks, so that the human operator could actually, focus more on optimizing the high level tasks. Yeah. Okay. So now, what the main purpose for this is also basically to recognize that in the modern, the new paradigm of robots and humans interacting, the roles are not repetitive, and we would like the robot to be able to make suggestions and to take away some of the load from the humans. Yeah. Okay. Now, what I'm trying to say is this, that one of the ways of actually trying to reduce the cognitive load of the human is to basically give some of the responsibility to the robots, and for the robots basically to take on, if you like, a partnership role in the task that the human is attempting to supervise the robot. Yeah. And for that to occur, the robot needs to be aware of the human's intentions, and basically to make suggestions for the human to basically to select. And in such scenarios, I'm proposing that we promote the robot from being a servant or a slave to something approaching a partner, but never equal to, but never supersede the responsibility of the human. So the human is always in a position to basically to decide on the suggestions by the robot, optimizing the task of the robot, and the human takes the responsibility. Yeah. But of course, you know, the sense is this, that when humans and robots collaborate in a general context, not only underwater but outside of water, they have many roles. Yeah, sometimes the robot partners the human. Sometimes the robot is basically you know, is working independently, trying to optimize on a subtask, and on certain occasions it might be requesting for assistance from the human operator. Yeah. Now, we understand from the past, from a long time, that humans and robots are not exactly the same. They have different skill sets. Certain things that are done well by robots, and there are certain things that are done well by humans. And in a task, we are trying to allocate responsibility. How do we actually do that? And when we recognize specifically that during the interactions, the relationships are dynamic, in the sense that sometimes certain tasks are much better adopted by the humans, and certain times they're much better by the machines. Yeah. Okay. So the issue is this, that when we are designing a user interface, I have a high-level task, I have low-level tasks. What do I allocate for each? So I could allocate the task based on what I assume that the robot and human does better. Yeah. But remember that in interactions, things are very dynamic, and there are certain instances where the human being requires assistance, yeah, from the robot, and sometimes the robot requires assistance from the human. So in all of these scenarios, we are basically trying to identify a new paradigm whereby the human gives up some of its responsibility, accepts suggestions from a robot, okay, to reduce its tasks and to put itself in a better position to optimize on the entire activity. In a traditional paradigm, you appreciate in ROV, the pilot does everything. He does the low-level tasks. He also concerns himself with the optimization. Generally, the robot does not request for assistance from the human. It does not observe or provide suggestions to the human operator. He just takes in instructions, if you like, blindly, okay, from the human supervisor. But I'm proposing that in a new paradigm, that to provide the human with a better opportunity for optimization and to reduce his cognitive load, he needs to promote the robot so that the robot takes on greater responsibility, greater optimization, and the robot needs to basically assist the human in some low-level tasks, so that it frees the human to basically to perform much better, if you like, system optimizations. Yeah, but for that to occur, we need to have effective human and robot communication. That the robot needs to understand what the human is attempting to do, and vice versa, so that they can work in a collaborative manner. These are concepts which are basically not so well imbued in underwater robotics, whereby currently the majority of the operations are controlled by the human being. Although some of these suggestions are being pursued outside in air, human robot interactions. Yeah. Now, what the presentation we continued on will be by my colleague Dr. Hui. He'll be talking about the simulator whereby we are developing under ROS to enable us to control a model ROV, which will enable us to model the operations of the robot and in this turbid environment, and also basically to share some of these concepts of giving a responsibility to other robots. Yeah. Okay. On that note, I will pass this on to Dr. Hui. Okay, Hui.
Thanks a lot, Popshit. Can everybody see my screen?
Yes.
So first, hello everyone. My name is Ben Quang Hui, and I'm currently a research fellow at Saab-NTU Joint Lab. And today I will present our recent underwater robotic project named Turbid Environment Object Perception. So with the idea from Popshit's talk, we can see that perception is very important for enhancing the robot to become a partner to human. And before introducing the details of our project, I first will discuss some of the challenges in this field. The underwater medium can absorb visible light and create a scattering effect. As you can see here in figure 1, where most of the visible range of light had a very high absorption coefficient. And this value will be even higher in the turbid environment. This will make the ambient light or illumination will become a very big problem. And even if you use an active light solution that is equipped to the robot, it is also not adequate because of the light attenuation, which means that your light system cannot travel very far, and also because of the effect called backscattering, which is shown here in figure number 2. You can see the light system illuminate the particles between the object and your sensor, or the open water behind the object instead of the object itself, which make your image resolution really bad. Another challenge comes from the sensor that you can use in this environment. There are basically 2 types of sensor you can use here. The first is optical sensor. This kind of sensor can only work in a very short range, approximately 10 meters in clear water, and it will be much less in turbid environment. Acoustic sensor, on the other hand, can work as a much longer range, and it is not affected by the water condition. However, the image resolution is pretty low, and it also be affected by the noisy environment. So how to deal with these limitations? Let's first take a look at the structure of our project. The first part of our project dealing with the robust object perception. To make the robot more intelligent as a human partner, it requires a robust understanding of the underwater environment to enhance its awareness, and also to allow it to safely navigate around. And because of the sensor limitation, we divide the perception into 2 parts, close range and long range. In the second part of the project, we consider the numerical simulation and the graphical user interface between the human and robot. The simulator will help us to reduce a lot of time and effort in designing and testing the perception algorithms. As you know, real underwater experiment is normally hard to set up, and also very costly. We also focus on the designing graphical user interface to enhance the operator-robot communication as an effective exchange of information. Now, first, let's consider the numerical simulation first. In underwater simulation, one of the important part is to simulate the sonar, and this can be done via different methods. In this case, we are using ray tracing to simulate the beams generated by the sonar. We also have to simulate the underwater environment with different water conditions, such as what the object look like in clear, in a mild turbid, or in a highly turbid environment. And finally, we also design a graphical user interface for the human to communicate with the robot. And with this simulation platform, we are ready to perform some of the algorithm for underwater perception. And first, we will consider the long-range perception first. Now, what is the problem relating to the long-range perception? In this scenario, the only sensor can be used is sonar because camera is not effective now. And even if your sonar can work at 200-meter range, one of the important problem is the limitation of the sonar resolution. So most of the state-of-the-art sonar on the market are multi-beam sonar, and the device send multiple beam at the fixed angles using a transmitter, and the return beam will be received by a receiver that is also on the sonar. So the number of beam will determine the image resolution. Therefore, the farther the object then from the sonar, then the lower the resolution you can get. As shown here by our simulation, on the left is our model with the beam from the sonar. On the right is the generated images. And as you can see at the at 5 meters, you still can recognize the shape of the object here with either cylinder. But at the distance increase, the image resolution reduced a lot, and at around like 80 meters, you can just see like some white spot. So now the object geometry or the shape, it become irrelevant in a long distance. How we are going to solve this problem?
Dr. Hui, we are running late, so can you please speed up your presentation?
So this is our proposed model. So instead of relying on the shape, we focus more on the ability to track the object. And if we are able to track the object, then we should be able to perform some object recognition tasks. So we start by eliminating the noise from the sonar data. And then we perform some kind of block analysis and association. And finally, we can track the object. And then we can extract some of the motion information from the object. And finally, we can perform the object classification. So in this video here, I just show some of the results that we got. This is actually a real data that we obtained from our Nanyang Lake. And the white spot you can see here is actually the fish that is moving around underwater. And we're able to track multiple fish and remove all of the background noise. So that's on for the long range that we are doing at the moment. For the close range, we can perform more perception tasks because we can obtain more information from the sensor. And then in this image, I'm showing the process of object reconstruction. So you can have multiple images from your camera, or in case a turbid environment, you can use multiple images from your sonar. And by capturing multiple images from a different angle, or you can capture it by multiple sonar, then you are actually able to recover some of the point cloud data for your object. And from this point cloud data, you can train a classifier to perform not only object classification, but also some pose estimation for the target that your robot is looking for. So that's all of the 3 main parts of the project that we are working at the moment. And thank you for your listening. And we are looking for some of the questions.
Thank you. Seat. Are there any questions we have?
No questions at the moment, Prof. Chai.
Okay, then we move on. Maybe we can come back a question later. Prof. Lu, I pass. Now I don't know whether you are ready to have your side.
Thank you, Dr. Chai, and thank you for a great presentation from Dr. Lee and Dr. Hui. Let's move on to Professor Modian and to Nina, because Richard is not here yet. Nina, are you ready?
Sure, I'm ready.
Okay.
I start sharing my screen.
Okay.
Can someone I think the previous speaker needs to stop sharing.
Yeah, Dr. Hui, can you? Okay, great.
Okay, beautiful. Thank you. Sharing, do you want to? Yes. Beautiful. Okay, this is my main screen, and I do from beginning. Okay. Hi everyone. It is my pleasure to present our work on our efforts on enabling long-term operation of underwater robots for climate studies. As I mentioned before, my research group focused on developing tools to address operational challenges of persistent large-scale deployment of autonomous vehicles in air, on land, undersea, and even in space. Today I focus our attention and my presentation to undersea persistent operations because the ocean is critical for our life, but it is not well sampled. Applications such as physical oceanography, Arctic observation, coastal surveillance, they can benefit from utilizing fleet of heterogeneous unmanned systems operating without human intervention. Why I am very much mentioning the human intervention is because today we are using autonomous underwater vehicles for a variety of applications. However, their operation becomes expensive and they have limited battery life. And because they have limited battery life, they traditionally come back to the ship or to the shore for manual retrieval and recharging. Now, there are other type of autonomous underwater vehicles that they are called, there are underwater gliders. They can operate for weeks or months, but they lack maneuverability. Our efforts strives to find solutions for both sides of these type of vehicles that they can be implemented to enable large-scale, long-term deployment of these autonomous systems for robust operation. We developed theoretical, computational, and experimental tools to address operational challenges, which includes smart autonomous energy maintenance for autonomous underwater vehicles. We enable in situ environmental response to data collection, and also we strive to bring down the deployment and operational costs. You see a variety of hardware that we have developed, including underwater glider, docking station, inflatable autonomous boat, and simulation environments that you see here for training robots and for navigational purposes and for object detection. So basically, we develop low-cost, high-value residential systems with efficient real-time control, which you see here. It is the autonomous underwater glider that we have, which is highly maneuverable. We develop integrated docking system and control for recharging and data transfer. We use machine learning techniques for robust autonomous performance, and we develop optimization techniques for mission planning and resource allocation to coordinate our assets together. All of these together will increase efficiency, endurance, while reducing cost. So let's start with underwater gliders. Underwater gliders, as I mentioned, are a specific type of autonomous underwater vehicles that they work based on change of buoyancy. They are very effective you see an example of these vehicles operating across Atlantic Ocean, and then traveling for 6 months and being very effective in ocean sampling. However, they traditionally lack maneuverability and modularity. And this has been our task to increase maneuverability, increase modularity, and enable them to work in high-risk area. High-risk area meaning in shallow water, and what shallower water than a swimming pool environment. You see our glider working, and I'm explaining how the glider works. It is modular. There are systems that there are parts. Mainly, we have a pump that it takes water in, and there is a battery that it adjusted basically the pitch angle, and the whole our components are on a rail that it rotates along the longitudinal axis and gives us the roll, which is very effective, and it gives us 3-meter turn radius compared to 10 meters and up of traditional underwater gliders. So now you see that we are very effectively working in shallow water of the diving tank of Purdue, and it is smaller in size compared to traditional gliders, and utilizing a feed-forward feedback switching controller, we are able to link steady flights. What do I mean by that? Look here, the gliders typically do a sawtooth pattern. Here we are connecting linear steady flights with turning flights, and then creating circular path S pattern and other patterns that usually aerial gliders perform. But we are capable of doing that underwater, which it gives us a new type of maneuvers that these vehicles can perform. Therefore, we can use them for new applications in shallow and deep water. So one of such applications here is a work that we have done with a company called Twinleaf, which they develop multi-mode sensor for object detection. And we basically characterized the Purdue swimming pool magnetic signature. So here is the swimming pool magnetic signature before we set the magnetic objects, and then we detected those objects in the water. This count as, and as you see, this count as a very noisy environment, and we could detect objects in this environment. We have then continued this work in lakes nearby for open water testing, and we are analyzing the data, and we will publish soon. So this is really a great achievement on our part, that we have developed a functioning vehicle, and we have used the modularity for adapting a payload, and also using it for a completely new application. We are continuing our effort in using and utilizing our underwater gliders. However, as much as we are pushing the boundaries of use of underwater gliders and using their efficiency, they cannot be used for applications such as this application, which is pipeline monitoring and mapping an area. For this, we need to use traditional propeller-based autonomous underwater vehicles. So therefore, we need to address their limited battery life. And for that, we set our sights in developing a vehicle agnostic solution for docking, where we can recharge and transfer data. Traditionally, the common and available docking stations are bulky, expensive, and they are very vehicle specific. So the question becomes, can we develop a docking station that it can cater a variety of vehicle sizes? The answer is yes. And we have achieved this through hours of simulation and optimization. And we have shown that we can cater torpedo-shaped vehicles of different sizes with our design. And the solution is basically this 2D docking station and basically a drop-in adaptable part that we put on vehicles and access the battery. For this to work, not only we needed to develop the hardware, we needed to develop the software. So the control strategy for docking maneuver, and to basically work and make sure that this works in challenging environments. So you see here the docking process, and here you're seeing that the fact that the design is so efficient that we can drag it and put it behind a autonomous boat, inflatable autonomous boat that we have developed. Now, the docking maneuver has two parts. There is an approach part, and then there is a homing part. The approach part, it is based on acoustic sensors to find where, the target. But then when we get closer for the homing, we use vision sensing to bring the vehicle home. And definitely we have successes and we have failures, and we need to be able to basically go around when we fail and we don't dock. So our algorithm has all this capability. Here, I want to show you one of our challenges for homing. Basically, initially we were going toward the brightest light. Okay, and remember that when we are docking, we dock traditionally in deep ocean. So brightness of the surface will not be a problem. What it will become is the murky waters and not recognizing the light. However, we also saw, because we were in shallower water and we wanted to challenge ourselves, we were adapting to the currents. We were doing very well in a lot of shallow water challenges. One thing was that the vehicle was showing us false positive. So the vehicle would mistake the sunlight and brightness of the surface for the light, and it would go toward the surface rather than going through the brightest light that we want, and the docking station was there. So therefore, we used machine learning techniques to be able to basically target and find the right target and eliminate other false positives. So there is a lot that it goes into the docking maneuver and different, how do we respond to what is our strategy to go around when we failed in docking, which I can go to more details if there is time. Now, when we have this, when we have a capable glider, when we have a solution for recharging, what can we do to have a fleet-oriented autonomy for area coverage and data collection? And that becomes basically an optimization problem, a mission planning algorithm for long-term operation where we need to recharge our assets. So we could have one docking station, or we can have multiple, which they are static, or we can have a mobile charging station. And as you see, it is possible with our docking station to have a mobile docking station. So basically, we want to coordinate our assets, and we want to find a placement of the static charging stations or rendezvous points of these mobile assets. We need to find efficient trajectories for workers and chargers, and we need to be able to handle the characteristics of the working robot and their charging time. Also, we need to handle failures. And you see that we have developed an optimization technique where the user gives the map. Yes?
Now we have 2 minutes.
I'll be on time. Given a map, we find this location, we minimize the total energy cost, and we ensure that we have a full coverage. As I mentioned, there is an optimization problem that we solve, and we have solved this with a genetic algorithm very effectively. That has two parts: offline pre-mission planner and an online real-time controller, where it responds to the failures or other challenges on board. You see the results, but however, this is where we have freedom of coordinating all the assets. What if we have a specific pattern that we need to go based on the sensor that we have on board? And for that, we have basically another strategy that we have developed for when the user gives us the pattern that their working robot needs to work, and we need to just provide the pattern for recharging. And we have implemented these on for coordination of surface water vehicles and underwater vehicles. We have shown that the rendezvous is possible for the assets to find each other and do docking. And then for showing the scalability, as you saw, we implemented that our coordination of ground and aerial vehicles, and we have shown that this is, online calculation and then implementation in water. Between aerial and ground vehicles. Moving forward, this is our plan. We want a heterogeneous system of systems working and using the best of each platform and working long term. And I want to thank our sponsors and great students that have worked on these topics for years and still enthusiastically are working on this.
Thank you very much, Nina. It's a great presentation. There is a question for you, but we wait until later on. We'll find time for you to answer. You can check the Q&A to see the question for you. Since Professor Richard Voice is here, we are going to introduce him to the panel, and he's going to cover in vivo, ex vivo, underwater robots for underwater agriculture. Thank you.
All right, thank you, Chung Sen. Apologize for my screwing up the time. I was thinking we were starting at 8:30, and but this is actually great because I was thinking, and I'm just going to blame it on Microsoft. I was thinking that I should be going after Nina anyway, because let me share my screen here, and that one. Okay. Because it makes sense from what talking about. Okay, so you should see that the is very much related in some sense, or at least inspired by work on the on gliders, yet is somewhat different. So I'm going to talk about it's an unconventional form of underwater robots, and that oops. So it's an unconventional form of underwater robots, and this is actually a new project we're getting involved in with the USDA. We've had a project for some time on CPS and precision animal agriculture, and that's what I want to talk about. But first, if you had a crystal ball in 1980, you would have bought Apple stock. It would have been illogical not to. In 1980, Apple, $1,000 of Apple stock would be worth about 20 million today. What we have is a crystal ball already for anyone who wants to see it, and that is precision crop agriculture. Because precision crop agriculture is really completely revolutionizing modern agriculture. And in the sense of this image, turning it upside down. Technology is providing actionable data that is being converted into dollars. But so far, it's been only working for crops. And the reason is this cow is Rosebud 23, or at least represents Rosebud 23. This is not actually Rosebud 23. Rosebud 23 was Brad Nelson's prized milker who worked, he was my office mate while we were getting our PhDs. I think you folks know of Brad, and the point is she had a name. And this was not uncommon 30 years ago, where every cow on the farm had a name because the farmers knew each cow, cared for them individually. We had much smaller farms, and the actual performance of the cow mattered. And that's true way back into when we started agriculture thousands of years ago. Because the individual lives of these animals matter, even though we're going to eventually kill and consume them. So I'm going to talk about, let me just, the point of this is what we're seeing is why has it been delayed? I think animal agriculture, precision animal agriculture, is going to follow that same track as precision crop agriculture, hence the crystal ball. Let me talk a little bit who I am, since I missed the initial introductions. First of all, my grad students say I kind of do everything in threes except daughters. I have 4 daughters, but I got my degrees are in 3 separate branches because I've always been interested in robotics. So I got BS and EE and MS and ME, and my PhD was in robotics, which is in the School of Computer Science at Carnegie Mellon. I've been at 3 universities and worked for 3 companies. I didn't go straight through in school, so I have some industrial work, but then also not just academe and industry, but I also spent some time in government. At the National Science Foundation, I was also at Office of Science and Technology Policy at the White House, and then have worked with Department of Energy on specifying their robotics roadmap, as well as a bunch of research projects. But the issue with agriculture is many of the projections are pointing to roughly 9 billion, some say over 9 billion people on the planet by 2050. This is forcing food production to double or at least increase by 90% in the next 40 years. There's actually a shrinking land base. Because of erosion, because of the expanding population is actually taking away space for growing crops. We need places for those people to live. We need places for those people to work. Climate change, of course, is enormous with weather events, pest pressures, and again, the number of people that are food insecure, right, continues to increase, which is ironic because if you also look at the statistics, we're actually making progress on hunger globally. And so when you put all this together, and there has been a historical trend dating back thousands of years that animal consumption increases with wealth. It's seen as a status symbol. Pollution increases with people. And as I said before, why hasn't precision agriculture affected animal agriculture the way it's affected crops? And that is because animals are fundamentally different. First of all, we care about them on the individual basis. In a way, we don't care about individual ears of corn or grains of wheat. And the closed loop timescales are much faster. And some of these statistics down here are, some of this is, we're looking at global consumption. You know, one of the indicators is, and when you put all this together, global consumption of animal proteins is increasing faster than the rate of population growth. Partly because, again, though all these things are coming into play. And in fact, if you look at just poultry, it's increasing, consumption is increasing about 3 times faster than population growth. When we look at the US specifically, you know, 50% of US land is devoted to ag of all types. Ag consumes about 10% of the US energy budget, 70 to 80% of all fresh water. And then you throw in the fertilizers, the herbicides, and things like that. And again, arable land globally is pretty much fully engaged right now. And at the same time, it's eroding. And so there really is no opportunity for expansion of growth as the population expands. And so the result is, we have been relying in the past on increases in productivity and that sort of thing, as well, productivity both genetically and mechanically. But there's many concerns that we're pushing our resources to the limit, including soil. And people are all about now, you know, the sustainability, the safety, and the productivity then of our food sources, right? From a climate standpoint, from the earth, and everything. So the bottom line is, animal agriculture is something that's really necessary. That many people say, yep, why? Because at least in industrialized countries, vegetarianism and veganism are increasing. Again, the problem is we're not, crops can't feed us, can't feed all of us alone. Animals convert indigestible proteins into digestible proteins. That's one of the benefits and why we use them. Again, the issues of why this has been delayed, and hence the crystal ball again, is that the time scales are measured in hours, not days, and times the number of feedings they get. And you know that you may not have a rain event in a large crop or operation for days or weeks. Same thing with feeding events, which is not true of animals. And again, what has happened in the industrialized farming agriculture with animals is we've lost that human touch. The ratio of animals to farmers has gone way up in the last few years as our farms, certainly in the United States, but this is happening kind of all over the industrialized world. And we're focused more on averages when we are, ironically, our populations care more and more about animal welfare and the individual treatment of animals. And again, I'm not going to, the cow is an example of a ruminant, and I'm going to talk just briefly of what the cow is doing is taking these indigestible grasses and things that, again, humans can't eat because of the high fiber content, and they have fermentation tanks, some of the most efficient on the planet, that convert these into basically human consumable proteins. And the chemicals that involve these are not well understood, actually. There are about 23 volatile fatty acids that are involved in this breakdown in a typical cow. We only focus on about 3 of those and really understand them. And so this is what we originally proposed in our project with the USDA in cyber physical systems, was basically CowNet, turning that data not only into dollars productivity for the farmers, but also happier and healthier cows. Because in fact, happy cows are 15% more productive than stressed cows. So this, again, this idea of stress-free is actually important. And to do that, you know, we've been investigating actually putting robots inside the cow's stomach. And the question is, why do we do that? Well, first of all, we need robots that are not damaging. And this is a big vat, a fermentation vat, as a, you know, from an industrial process standpoint, that's what they're doing to digest. And so this is in the in vivo application of underwater robots. And the issue is, the fermentation vat is actually very complex chemically, and it's a number of actual strata where you have hard material up top that is starting in the digestive process down to what's virtually clear water at the bottom. And so the strata are important for measurement. And so mobility, which is the hallmark, of course, of robotics, right? Mobility is actually important and key to being able to understand the health and metabolism that's going on inside the cow's stomach. And so this is actually a slide just from a paper we recently presented. One of the things that we focus on in my lab is reconfigurable and modular robotics using heterogeneous module combinations. So what we've started to do is develop, and here are just some things used for various ground emergency response and some DOE applications in nuclear processing. But what we're starting to look at is a buoyancy-based robot for the study, again, of these chemical processes within the cow's stomach or rumen. And the idea here is very much like the gliders that Professor Mahmoudian's develops, right? The idea is using to achieve locomotion, using very slight changes and low power changes for very long duration missions. The issue is, though, Nina has the ocean, right? Or at least large bodies of water. And we have the opposite, right? We have a very constrained environment. Of course, our robots are much smaller, but the issue is, how do you then control the location as well as the pose? Because often we're trying to take these sensors and get them in specific areas, strata and locations within the rumen, because it's not only differentiated vertically, but we want to get all around the rumen to create basically an observatory. And an interesting thing is then, if we talk about a neutrally buoyant vehicle, we can just control with very slow actuation the attitude of the robot. Articulate the center branch of the robot, much like Nina uses sliding masses to change the orientation in her glider. That actually controls we can use that to control the orientation of the vehicle. And then by using either morphing, think of for years, people have been talking about deformable wing airfoils. These are essentially now use a soft body of the robot as hydrofoils, that while we slight changes in the buoyancy, which again are relatively low cost from a power perspective, we can then use the vertical rising and falling, much like a glider, only we'll first use what we refer to as buoyancy gates, by changing the orientation and simultaneously with the up and down buoyancy, we can actually affect locomotion, and in this through all 6 degrees of freedom. And the simplest way to think about it is a Manhattan distance kind of approach, where you first move in the X, move and use undulating Z translation to move in X and Y, and then while you're also individually changing Z. Z. And but we can also do this in a concerted effort, much like Nina was showing about how to plan the neighborhood trajectory. And so we've started doing this through originally some prototypes that are rigid. So what we have here is the 3 paddles here are actually buoyancy, they're little bladders. And then there's some mass associated with the main central robot, which is a 2 degree of freedom link. Notice that they're roughly kind of shaped like airfoils or hydrofoils in this case. By tuning those angles, right, and changing the orientation, we can not only change the orientation of the entire robot, but we're simultaneously changing the orientation of the fins, not independently. The fins are just attached to the body, but that changes the orientation of the fins, or at least these surfaces, when we move to a soft robot morphology, but which we're doing for biocompatible purposes. But the idea then is through these oscillating vertical actions, much like gliders do, of using this to, in a low power mechanism, position these sensors as we need. Now, the interesting thing is, while this is going on, the rumen goes through contractions. And ultimately, we want to also capture, and so those are very large, think of these as big ocean currents, waves, if you will, if you were at the top, because the entire rumen churns on a periodic basis, which is going to dominate these relatively low forces. And ultimately, we want to use that to also help us locomote in a global sense. And here's some initial, with this rigid prototype, some initial examples of how the robot through our simulations, through changes in that central articulating joint, we can actually change the again, that orientation. And then of course Z is modulated by the buoyancy, by simply taking in and out little bits of water.
Dr. Voice, 2 minutes.
Thank you. Another application of this is the ex vivo approach. Again, the idea is we may want these to survive for years inside a cow, and that's in one of the applications then is aquaculture, and an example is shrimp ball, what we call shrimp ball aquaculture, and this is an ex vivo monitoring, where now in this rendering, a shrimp ball, a commercial shrimp ball, basically is a coagulation of shrimp, much like cows or social animals. Even shrimp, which don't have very large brains, we're talking a small number of neurons, but still they do have emergent behaviors from their social activity. And so this mass in even a commercial fishing shrimping operation, where they're cultivated, they're isolated, they're in the ocean or in a large body of water, but isolated usually with a cage or something, yet the shrimp tend to ball together. One thing, but these may be very large. These could be 100 meters in diameter for a large shrimp ball. And an interesting thing is the activity of the shrimp is as an emergent behavior from this entire ball of shrimp. tends to increase in activity when they are ready for feeding. And so this is an important to optimize feeding. They also have different predatory responses. And again, they're exhibiting emergent behavior or social behavior. And we have the same issues in this case. We can have a larger robot, but still relatively small compared to the shrimp for, again, low power, long duration monitoring. And so, kind of in summary, underwater robots, I think, for animal agriculture is this crystal ball that we've seen from precision crop agriculture. This is telling us this is going to be huge. And it's an important area that hasn't been highly investigated because of those issues that I mentioned earlier on why animals are different. But we can use underwater type robotics because mobility is key for sensing on the individualized basis to return this sense of individualized care for animals, both in an in vivo case and in ex vivo monitoring of entire herds. All right, so thank you.
Thank you, Dr. Voice. If you have questions, you can leave your questions in the Q&A section on the bottom of the slides or on the screen. I will give the floor to Dr. Chai to introduce our next outstanding presenter. Thank you.
Thank you. Next, we have Mr. Yen Seesyu from Sweden, and he is the chief engineer and going to share with us from the industry perspective for underwater robot. Thank you.
Okay, thank you. See if I can share my screen here. Okay. Is that showing up?
Yep, we can see it.
All right. Okay, so what I'll be doing is giving you a sort of review from the industry point of view, or more specifically Saab's point of view, what we are doing and where we are seeing things going in the underwater robotics world. So a bit of background on my part. I'm a chief engineer for Saab-CI, and I've been working with ROVs, i.e. on remote operated vehicles since, too long really, 80s, 90s, last century. So I've been around for a while. Saab is sort of active in this area in a few key areas, and one is what we call MCM, and that's mine countermeasures, clearing mines and other nasty things from the seafloor. And the other is, of course, commercial stuff, and probably a lot of you know that a lot of that has been traditionally done in the oil and gas industry. Wind farms are growing rapidly, and as the previous speaker also talked about, aquaculture, i.e. fish farms and stuff like that, is really growing very quickly these days, and a lot of our sales are going into those areas. In these fields, we have everything from traditional remotely operated vehicles to AUVs, subsea resident vehicle systems. A bit of a view backwards. You probably know RVs have been around for a long time. I think the first ones were developed sometimes in the 50s. And some of them came from the US, like the RCV225, sort of top left, which is considered to be sort of the origin of the eyeball ROVs. Then you have everything from sort of stuff like in the middle. It's a very agricultural sort of thing, hydraulic vehicles, which are not very intelligent at all. Basically a agricultural tractor with propellers instead of wheels. And to the far right bottom, you have old first attempts at actually doing autonomous intervention robots like the Alive from the cybernetics. So, and these are things from more than 20 years ago. So you can imagine people have been at this for a while. If we then look at where we are, what our customers look like, it's a very sort of wide and varied bunch. So what you see on the picture there is your typical ROV operator, small ship, vehicle, and they do sort of all sorts of things, finding things, scanning things, poking things. And we sell a lot of small size vehicles to this sort of customer. Another big sort of customer we have are the oil companies or the energy companies, as they call themselves these days. They, of course, set a lot of the standards and decide what they need to sort of expand their and grow their business. We have a typical control room. You have sort of nice environments, that sort of thing. You have a typical ROV setup, lots of tools. People use these things from everything from survey to trenching to finding things. So the sort of flora of available options for this is quite enormous, and that's a big thing for any ROV or underwater robot producer. We need to be compatible with a lot of the weird and wonderful things. On the military side, we have, of course, stuff that's need to find and clear mines. And there are additional requirements with respect to signature, to sort of a lot of specific military things with explosives, that sort of thing. We have some interesting cultural differences. So we illustrate this with a truck from the US, where big is beautiful. We have in Europe quite a different culture where people are more oriented to smaller things. This is something that we need to take into account when we sort of address our market. Some of our customers have lots of space and don't see that as a problem. And some of our customers work on submarines, where, of course, every square or cubic foot is important. We have everything from frozen to sunny environments, and of course a bit of bad weather mixed with calm seas. So it's a really mixed bag of things that we need to address. And since Saab is roughly, according to our own estimates at least, on the segments that we covering 50% of the electric ROV market, we need to sort of fit in all of these different places. And on top of that, we have a lot of sort of requirements, standards, and things like that to cope with. So how do we do this? We have a sort of a toolkit. We have different vehicles. We combine them with the different other modules, tools, control system options, simulation tools, etc., to produce something that our customers can work with. And this is sort of one of our illustrations of what our customer world looks like, right? At least for now. You have pretty big support ships that deploy ROVs. So you have sort of wind farming energy stuff with the smaller ships or USVs. You have the traditional ROVs doing intervention on the seafloor. You have our Saber-Tooth, which has been in some of the early presentations, which is a sort of a hybrid AUV ROV that can be used in a lot of cases. In this case, it's used in an untethered autonomous manner. But this is the way it is right now. But what's happening is people don't like these things because they are expensive. Big boats cost a lot of money, they require a lot of crew, and there's simply no room for that going forward. So we want to eliminate the big ships, and we want to eliminate the platforms because they are subject to weather and all sorts of interesting problems. And the idea of many in the industry is that everything is sort of going subsea. And one of our big customers, Equinor, is talking about what they call the subsea factory, which is basically putting everything that's going on the seafloor. On top of that, of course, we have aquaculture, and top left now is a huge container that's being towed out to basically farm fish. And connecting back to what the previous speaker was talking about, this is a highly industrialized thing. And I've seen presentations from NTNU in Norway, for example, where they are actually capable of identifying individual fish based on retina scans from afar. So there is a lot of stuff going on in this field. The interesting thing for us, I would say, is that people are thinking that, okay, if we're going to do all this underwater, why not put it all in the same spot? So co-locations is a thing where we are actually building sort of industrial parks, if you like, but subsea. So in the North Sea, Equinor and others are spending quite a lot of money putting infrastructure in place with communication, with power, etc., to support this, and that's going on right now. To sort of illustrate that, this is a slide I was stolen from Equinor, and this is sort of their view of pretty much the same thing. And as you can see in the bottom, the very clear goal with this is to save money. They need to bring the cost down, otherwise this is not going to be working in the long run, and especially for supporting, how to say, renewables and agriculture. They cannot support the traditional oil and gas way of doing things. Another aspect of this is, of course, that these things need to communicate, they need to be controlled, and the old standard way of doing this with a ship and wires to a control panel isn't going to work anymore. So everybody in the industry is digitalizing or moving to the cloud, or there are many names for it. And this is also quite important for us because we need to fit into this. It's no longer sort of we can't deliver a to B turnkey system. It needs to fit into this big picture with interfaces and infrastructure. And of course, it's not only on the water. You have stuff on the surface, more and more USVs and drones supporting things from above. You know, all of this needs to sort of end up in the same system. So another slide that's stolen from Equinor, and this is sort of just to illustrate their view on the time scale of this. We are sort of in the corner here. This is a 2-year-old slide, in fact. So we are here where we can put stuff on the seafloor, but they are looking to expand this and more work to sort of remote operated autonomous or semi-autonomous systems doing most of the stuff on the seafloor. So the trends then is, as I said, cost reduction. I mean, that's the key. That's what's driving everything that's going on. If it doesn't lead to lower costs, it's not going to happen. So as I said before, traditional operations are too expensive. You can't do it with a big ship that costs you, millions a day to operate. So you need to put stuff in smaller ships or preferably USVs or preferably on the seafloor itself. And as I said, this is really important for the emerging things like renewables and like aquaculture. CO2 reduction is really big. Everything we do is sort of focused on reducing this. And of course, it's a lot cheaper and better from a CO2 point of view to be subsea resident than have a big 150-meter ship sitting on the surface. Remote crew, everything needs to be done from afar because you don't want people on small things in the middle of the ocean. You reduce overhead, and of course, this poses a bunch of new requirements on our things. As I've mentioned before, you have these offshore industry centers or things coming. And if we look at them, why is this all of a sudden possible? And that's, of course, that there's been a lot of things improving on the energy side. I mean, batteries have been developing rapidly the last few years. Communication, same thing. There is quite the good things these days to be able to communicate acoustically and remain in some degree of control, even if you are not tethered, right? You can operate stuff through satellite links due to sort of improvements in control systems and autonomy. Infrastructure-wise, then of course, before everything was more or less sort of just a bunch of metal sitting on the seafloor. Nowadays, it's built with fiber optics, with power, etc. There are a number of companies starting to produce buoys that can support autonomous and other vehicles out in the middle of the ocean. We have large USVs, a number of companies that are getting heavily into that, developing 24 to 36 meter big USVs that can be operated over the horizon. Drones, of course, they are getting better. They can support lifting things in the sort of few hundred kilos up to a ton these days. And of course, cloud-based operations. So, summary of this is really what's valuable for our customers, and that's they want work done. They want it to be done 24/7. And they don't want hiccups on the way because rescuing failed vehicles is very expensive. So key to being able to do this is to make reliable stuff, right? And as that happens, we need to be able to service these things remotely. And at the same time, of course, bring costs down. And fortunately for us, we are doing the things that are actually performing the work. And I think that the big cost reduction these days is actually eliminating the large ships. So some examples of the future. Top right, you have something called the subsea shuttle, which is something Equinor are currently looking at. And I don't know if you can see it on the picture there, but they are looking at doing huge underwater drones, 130 meters long roughly. And the point of this is to be able to transport CO2 back out into old oil and gas fields and re-inject it into the ground. So this is a huge project in Norway right now. We have bottom right, a company called Ocean Infinity, which are investing heavily now in building a armada, a big fleet of large USVs, where Saab vehicles are a part and sort of operated from these. The goal of this, they are being built as we speak and are going to be operating in the next years, doing everything from survey to intervention, remote controlled over the horizon. on the bottom, we have our own vehicle doing a approach and docking to Equinor's standard docking station, which they now have placed on a number of spots in the North Sea. And the conclusion is this: we're not thinking of just doing things, old things in a new way. Because of the drastic reduction in cost of doing things, a lot of things which were completely out of the question 10 years ago are all of a sudden possible. So I think we'll see quite a lot of new requirements or ideas for what can be done with underwater robotics due to the fact that it's becoming more accessible. And I'm happy to see what you guys are all doing, and what a lot of this is about is being able to bring new technology underwater, development on batteries, on autonomy, on communication, on everything. A lot of it is driven by stuff that's going on topside, so to speak, but it needs to be adapted and tweaked a bit to be useful underwater. And as I said, starting off, this is not only about autonomy. Autonomy is a small part of it. It's about very much about mechanical engineering, reliability of stuff, how you use it, applications, new ways of thinking. So yeah, I'm thinking this is a good start for at least Saab to have this cooperation with you guys. All right, I think that's it for me.
Thank you. Thank you for this exciting and insightful presentations. There is a question in the chat. We are behind the schedules. For the interest of time, I suggest we have question and answer mode to the end of this webinars or through this chat kind of scheme. Next, I will time over to Prof. Lu again.
Thank you, Dr. Tsai. The next presentation is from Professor Ming, B.C. Ming. He's going to, from Purdue University, he's going to cover the topic regarding robots for sediments and samples from lakes and rivers. Dr. Ming?
Yep, thank you. Okay, let me share my screen. Just give me a minute. Okay, can you see my slide?
Yes.
Yes. Okay, hello everyone. My name is Byung-Chul Min, and I go by BC. I am associate professor here at Purdue University. And today I'll be talking about our recent collaborative researches between Purdue University and UNSA at Peru about robotic sediment sampling system. And what is sediment? Sediment is the compositions of solid particles of mineral and organic materials. And sediment can be transported by water, wind, or even ice, and eventually deposit at the bottom of a body of the surface water, such as river, stream, lakes, and reservoirs. And sediment is the most common pollutant in water bodies, and it has significant impact on social, economic, and ecological systems. So therefore, sediment monitoring and management system is necessary. Sediment sampling is primary task for sediment monitoring and management. And traditionally, sediment sampling task can be done manually or semi-autonomously. However, it is time-consuming, labor-intensive, and also costly. Therefore, the goal of this research is to develop uncrewed sediment sampling system for sediment sampling from surface water bodies. The main idea is using multiple robot teams consisting of an uncrewed surface vehicle, as you see from the slide, and I will call it as USV throughout my presentation, and underwater sediment sampler, USS, or sampler, I will call it throughout my presentation for sediment sampling. So the USV is the main control station, and it needs to transport and launch the sampler. And the sampler, USS, is the sole platform for underwater sediment sampling. First, let's take a look at USV. You see upper part over here, uncrewed surface vehicles. The main task of a USV are transporting and launching the sampler. And one of the major challenges for this task is how can we minimize the maneuvering of the USV during launching the sampler, and also why the sampler is sampling sediment. For positioning task, we developed the customized winches and adopted a double anchoring method. God bless you. Okay, and for launching and retrieving sampler, we used heavy-duty winches. So now you see that winches is on the USV, and then using winches, we can launch the sampler, but also we can retrieve sampler to the air. The developed USV is a pontoon type. Its length is about 3.8 meters and width is about 1.4 meter. It's a huge USV. And let's move on to the sampler, USS, underwater sediment sampler. And main task of the sampler are launching and sampling. Numerous challenges are involved, but notable challenges are how can we design the USS as submergible platform, and how can we waterproof the sampler, and how can we secure the sediment sample from contamination and lost, and also how can we collect high quality of a sediment effectively. Once again, our system has two main missions, which are launching and sampling. And it has three subsystems. First is core sampling pattern system. And second is sensing system. So we have number of sensors inside our samplers. And last is monitoring system. So this is mainly for human operator. We designed our sampler so that it can be submerged by its gravity only. This means that it doesn't require any propulsion power. So for stability, we designed the sampler so that its center of gravity should be lower than its center of a body. And waterproofing is so critical. So we put great amount of effort and time to ensure waterproofing for our sampler. And we used rubber ballers to enable linear motion for sampling core. But because of that, we had to equalize pressure inside sampler. Otherwise, like you see from the slide, the rubber ballers become deformed as it enters deep water. So for these pressure equalizations, we used syringes and it worked pretty well. And sediment sampling pattern is so important because it has huge impact on effectively collecting high quality sediment samples. For example, in order to collect samples, penetration force must be greater than reaction force applied to the core. And sampling pattern is highly affect penetration force. So if you'd like to know more about sediment sampling patterns, please refer to our recent publication. We carry out a preliminary study and came up with effective sampling pattern that is combination of linear motion, rotational motion, and hammering motions. We designed our sampler so it can generate all these 3 motions. So here is a quick demo video of our proposed sampling pattern. Oh, sorry. Now you see that sampler is going down using linear motion and core is rotating. And then if you hear some tuck, 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 that is sound coming from hammering motion. And when core is being retrieved, we only implement linear motion. So now is sampler core is now coming back to the original position. Just note that now we tested these sampling patterns in the air, but the sampler is supposed to be walking underwater. And we designed passive gate so that we can seal the bottom of the core sampler to prevent sample loss and also contaminations. Now here, core is now being retrieved. And then now gate is closed so that we can prevent sample loss and also contamination to the other. We carried out a field test at local water body nearby Purdue campus. So here you see water retention pond in the United States. And here you can see the experiment setup. We see here, you see a base station and also complete setup of the USB and also sampler. You can see sampler over here. And let's watch this video that shows one of the field test. Now the USB is moving to the desired sampling point. So moving to the sampling point. And then once it reaches it launches anchors. Now launches the sampler to the bottom above the water. And then now sampler start penetrate the sediment with the core sampler. And then sampler is being retrieved. And then gate is closed. And USB is retrieving the sampler back. And then now you see the collected sediment. And once it's done, then USB returns to the base station. And here are trajectories of our USB during deploying red lines and positioning. So while the sampler is collecting sediment at the bottom of the water. And let's watch these videos that shows USCV and USS sampler monitoring view the more closely during the sampling process. Now, oh, did you hear me? It seems like I'm muted. I don't know. The host want me to mute?
No, we can hear you.
Okay.
Hoffman, but we don't hear any sound from the PowerPoint. Just you.
Yeah. Okay. Good. Yeah. I just muted the sound from the video. So yeah, then it's okay. Good. Okay. Now you see some closer look of this experiment. And here are the collected samples from the experiment. As you can see, we could successfully collect sediment sample from our test. And the core, this core, was designed to be penetrate 200 millimeter, 20 centimeter riverbed, but we couldn't get that amount of a sample from this experiment. And that's because little lifting of sampling body occurred. But that being said, experiment went pretty well. Before closing my presentation, I'd like to share some lessons from that we learned from this experiment and these researches and field experiment. As you expected, we couldn't make successful cases all the times. We also faced numerous failed cases, and those failures happens due to multiple reasons. And first, sometimes there was nothing collected inside the core. It could happen with many reasons. One of the common reasons would be when sediment is too hard and the core cannot penetrate it at all. Or when the riverbed is not flat, so our sampler cannot settle at the bottom of the riverbed stably. Also, sometimes we are able to collect a sample, but we lost collected sediment during retrieving phase, as sediment was coming out from the core bottom. Next, sometimes we lost communication between the base station and USV. Also, algae and vegetation, algae you see from the water, and vegetation became obstacles to our vehicles. And lastly, it rarely happened, but one time cables from winches were tangled with the other communication cable. And our system is currently in Peru, and I just came from Peru, December. And we plan to improve our systems to be more suitable for Peruvian environment. This is all my presentation. I'd like to thank my team at Purdue, and Unsa, Richard is here in this webinar. And also I'd like to thank our sponsors, Unsa and also NSF, to support these researches. Thank you. I will be happy to take any questions.
Thank you, Dr. Ming. You are ahead of time. Great. So we'll make it on time. We actually have like 2 minutes left. Do you have any questions, or you want to put your questions in the chat section? That would be great too. I'm going to give the floor to Dr. Chai for him to introduce our next outstanding presenter.
Okay, last but not least, I will have my colleague, Dr. Bosman. He is also the co-principal investigator for the underwater robot project. Dr. Bosman, are you ready?
Yes, can you see my screen? I'm sharing it.
Sure.
Okay. Thank you for all attending at this hour. I'm sorry I missed some of the talks. Some are very interesting. Today is a Friday night in Singapore, and I was invited in a wedding that just ended a few minutes ago. And I want to start with a little bit of history. How did I end up here? I'm an aeronautical engineer by training. All I did in my life was aircrafts. And then somehow or another, I was lured into the world of underwater autonomous vehicles. I met in 2014 a CEO of a company that's doing oil pipeline inspection in the Mediterranean. And he basically was able to convince me that an AUV is very similar to a airship. In fact, they have the same governing equations and same modeling. They both work in undeterministic and chaotic environments. One is just in air as an airship, and the other is working underwater. Also, the water conditions are pretty bad. Furthermore, he sort of told me underwater, you have no communications, you have no GPS. So your challenges are much, much higher. And he challenged me to start this work. So I thank him more than anything. And basically, when we started the work, he started explaining to me how much he's paying to obtain ROVs, which is the figure of a traditional ROV I'm just showing you right now, and how much he was paying for his top ship or his surface vessel in terms of the cabling, in terms of the transportation logistics, the rent of the boat, and how much energy it was costing him. The alternative of using an ROV for inspection work was not there, being all electric or autonomous at the time. Because autonomous vehicles, they more or less look like torpedo-shaped vehicles. They only have 1 degree of freedom. They're really not good for light intervention work, just maybe inspection or surface mapping. So we were tasked in 2014 as a university to start thinking of making a vehicle that was all electric, hydrodynamically efficient, because now we really want something that doesn't have a lot of drag and not a lot of resistance. He had the requirement that the vehicle had to be untethered because he was operating in the Mediterranean, in the Gulf of Aqaba, and in Southeast Asia here. And he wanted to have an easy way of logistics of moving his ROVs around. We basically started a group of enthusiasts where we wanted to find vehicle equations to enhance the performance of the vehicles. We had an in-house group building an AI management system for the vehicles at the time. And of course, we are considering at some point hybrid power also with an all-electric vehicle. And I will come to this little AUV that we just manufactured, or the company manufactured last year, and it's now in operation, which is one of the first success stories. But to do all of this, we wanted to do like a model to do a performance analysis or to reduce the drag quite a bit. We really needed to understand how to calculate the different terms governing the operation or governing the vehicle dynamics. And just 1 or 2 slides of equations. I apologize for the heaviness. It's basically Newton's second law of motion. the mass times the velocity, the rate of change of velocity, plus some damping multiplied by the velocity and the drag and hydrodynamic terms. But what's interesting is that the mass is not the mass of the vehicle. There is an added term, which is known as the added mass. Because vehicles are neutrally buoyant in the water, they're accelerating as they're moving in the water, they're accelerating the water, and we have to account for the forces generated by this. The added mass term in general is a matrix 36 terms, sorry, 6 by 6. And if you design the vehicle with good degrees of freedom on symmetry, you can have many of them equal to 0. The only two terms in here that I will mention in this presentation, just for the shortness of time, is a term which is related to the surge. Surge is the motion of the vehicle in the forward direction, and a term which is related to the roll. So it's how the vehicle sort of rotates around the x-axis. So in brief, finding the added mass, there are two techniques. Either you go through experimentation or numerical. Experimentation is a very expensive process. It's usually done in a tow tank using a PMM test. Tow tanks are basically very large swimming pools with a very complex apparatus holding the vehicle. In this picture, it's a ship, but if the vehicle is submerged, it's an AUV or a submarine. This apparatus on top gives embedded motion to the vessel, whether it's adding an oscillation or adding a degree of freedom of rotation in any one of them, and at the same time measuring the forces. So it's quite a complex measurement technique. Not only is it complex, it's also very expensive. Maintenance of these pools is becoming quite difficult. Of course, the alternative, which is simpler, is a pendulum test. The pendulum test, however, doesn't determine all the coefficients, as I showed you in the 36 terms in the matrix. Alternatively, we can go numerically. Numerically, one of the methods is doing the equivalent of the tow tank, which is, I call here the simulated PMM or the unsteady inviscid flow simulations, where we basically can embed inside a numerical domain a vehicle, and we can impose the motions just like the motions created by this complex mechanism that's used in the tow tank. And we can embed those motions inside the computational domain and compute the forces, and from these forces go backtrack and calculate our added terms. And of course, we need to know that we're right. So there's another simplified model known as the potential theory, which is used just to validate some of the terms. Just a simple idea. We start with a vehicle. Here I'm just showing like a soap bar, a vehicle just for simplicity. We mesh it, we embed it inside a mesh. This mesh has a dynamical capability of undergoing any motion that we want to obtain. For example, if you want to do surge motion, then this vehicle will be, you will add to it an oscillatory motion in the X direction. If you want to do a heave added term, you would let this vehicle move upwards and downwards. And so you can actually explore every single term. Modern computational techniques, if I had time, I would talk about them in more depth. But just in brevity, we're using something known as an overset mesh, where we can add our vehicle inside a mesh, and this mesh could be given any degree of freedom of motion. Then we post-process the results, and we use some form of Fourier decomposition to find the different added mass terms. Going forward, we have to validate our results, and even though the potential theory has been present way before the simulated PMM test that I'm showing, one of the disadvantages of the model is that it cannot be used to calculate the drag terms. And since we want to do performance analysis in the future, we needed to validate our Inviscid unsteady simulated PMM. However, we use the potential flow theory just to verify or validate some of our calculations at start. So going back, we started by saying, okay, let's build a vehicle. So this vehicle we built in 2015. It's a nice small vehicle, only about 1 meter in length, 30 or 40 kilograms in weight. And it was well instrumented at the time. We built this vehicle and we went ahead and we calculated the added mass terms. And we found that our added mass term, as shown here after doing some analysis, was 6.2. And when we did this added mass term, even though the first vehicle here is the complete vehicle that basically was operated in the swimming pool, we did it for a simplified geometry where we removed those legs and we removed all the frame supports. Using the potential flow theory, we got a number which was similar, so we were sort of happy. Our numerical codes that are pretty complex are resulting in similar results. However, we got a shock in our life when we found out that adding the frame supports and adding the rotors and even adding the openings for the heave thrusters and the different degrees of freedom actually affected the added mass terms significantly. This for performance studies, just to sort of elaborate, this change can result in a 15 or 20% change in power requirements, for example. So if you want to operate autonomous, all electric, then your mission planning is totally messed up. So we had to do some form of parameter estimation. So our vehicle, we basically did a lot of tests. This was in a swimming pool where we would give it different inputs, whether pitch input, roll input, or yaw input. Using just an INS or IMU, we were able to calculate the different roll rates, pitch rates, and yaw rates. Basically, we couldn't look at the surge coefficient, at least in this first model that we started off with, because we didn't have our ROV at the time equipped with a DVL, which could measure the forward speeds. So we only had an INS, so we could only measure accurately with confidence our rotational angles. However, regardless, the potential flow theory predicted that the simplified geometry had a coefficient of 0.3, the complex geometry was 0.42, so that's including all the propellers and all the frame. So the big question that we have is which one's correct. So we did a very simplified analysis where we said, okay, for a pure second order system of pure rolling, we can actually write a simplified form of the equation. And this simplified form of equation includes the added mass terms. It includes the damping terms, which are both the drag and the Coriolis, which has an added mass term as well. And using the experimental data, we can basically obtain the both the damping ratio zeta and the undamped natural frequency, or sorry, the damped natural frequency omega d. So the damped natural frequency is simply obtained by getting the power spectrum for the vehicle in different dynamical tests, and where the mean, where the peak was for the different tests, we simply said this is the location of the damped natural frequency. From geometry and from our understanding of hydrodynamics and the design of the vehicle, we can go backtrack and obtain our added mass term for the roll, which turns out to be, roughly speaking, equal to 0.4, which is similar to the complex geometry. So the first lesson that we went ahead in the forward work, which I'm not presenting here, is that we really need to take into account all the complex features of the geometries of our vehicles. We've been able since then to develop quite a bit. Just to close this story and to say a little bit about the success, this work started in 2014 by the CEO of a company asking me in the university to start this work. Since then, I've left Egypt. This work was done in Egypt, and the company since then, I've become more or less a supervisor for master's and PhD degrees there. But I'm proud to say that the collaborators that ended up doing all the hydrodynamic work and all the measurements are the 5 of my students shown below. And they've come up just last year with their first commercial product, which is a nice handheld ROV, which has a point cloud 2-camera-based system with everything integrated inside, a very nice operable machine. And they're soon going to launch a bigger, more advanced, nearly 1-ton machine that is purely autonomous, untethered, fully battery operated. So I wish them all the luck. What's coming in the future is that we're starting to equip all of our ROVs with DVLs, and we're starting to use a real-time assessment during the mission to estimate the added mass coefficients so that we can always, using an artificial intelligence system, improve the performance of the model on the fly. With that, I end my presentation. And I hope I didn't exceed the time. I think I have 1 minute to go. So I hope you all enjoyed what I was trying to say and my message was clear. Okay, thank you.
Thank you very much, Dr. Basman. We indeed have a few minutes. Let's invite question. Question from audience or question from panels?
I'll ask a question if it's okay to Mr. Ciejo. I posted this in the Q&A. There was an apparent a snake-like vehicle or something you had on one of your slides. Can you expand on that a little bit, if I'm correctly?
Yeah, that's as I said before, we have quite a good relationship with Equinor, and this is a Norwegian vehicle developed up at NTNU called Elume. If you Google that, it's EELUME. So its origins were actually an idea that you would have a snake-like vehicle sort of propelling itself like an eel. But the present incarnation of the thing is actually propeller powered with 1 or 2 joints, mainly focused now on adapting it for doing things rather than swimming. So you can say it's one of the possible approaches to getting benefit of having a sleek, low drag body for the transport phase and being able to change shape into something that can do something when it's in place. There are quite a lot of YouTube videos and things illustrating what they are thinking, but it's a experimental thing at the moment, so it's not something that's a commercial product as yet.
Excellent, thank you.
Professor Min, I have a question. The project you are doing is quite interesting. Back to in Singapore, we have Singapore is an island country, but freshwater is always an issue. So we have many reservoirs. Some of the reservoirs are like marina barrage. Actually, always they are issued how to check the quality of the waters. So your robot, maybe whether you have any other research relevant to those water quality kinds of measurings.
Are you asking me or asking in general?
Yeah, I'm asking Professor B.C. Ming.
Okay.
Oh, I'm so sorry. Can you repeat the question again?
Okay, my question is for freshwater qualities, whether your current research, you have some other research relevant to the water quality measurement?
Yes, we do. So today I presented more focused on sediment sampling, but in our lab, we also do research on, let's say, water quality sampling as well. So we developed different types of USV, unmanned surface vehicles. So it's more, one type is very small, let's say portable, so that we can just throw it into the water body. So the platform can do some water quality sampling and also water quality monitoring. And also we do have some relatively larger size of it, but not really large. It's about 1 meter. But we do have also that platform can do water quality monitoring and also even algae collections, some vegetable collections, and even some trash collections, those types of things.
Thank you.
Maybe I can add to that and say that among our customers, it's quite a common thing, or one of our biggest customer is an Italian oil company. That they have a specific program for what they call clean sea, where they use vehicles like the Saab-NTU to actually do large scale water quality monitoring, sampling water, sampling pH, sort of the CTDs, you know, all the sensors you can put on the vehicle really, and scanning areas to make sure that you are keeping water quality within limits.
Right. Are there more questions for the panel or for our researchers? Well, I think if there is no more questions, we know how to contact with each other. And Dr. Chai, shall we move to closing remarks?
Sure.
Oh, okay, let me go first. And first of all, I really appreciate all the presentation. The speakers have done a great job and sharing your research outcome, products, ideas, and we have exchanged a lot of good information today in the early morning, late night in Singapore. And I also appreciate the efforts from all the administrators from both sides, from Purdue and NTU, to support this webinar. And we have our Director of Globalization, Baraha, is here, Ms. Baraha is here, and Dr. Carey, our Dean. Also, we have Michael and also Dr. Tiao. And also we need to especially for our appreciation to Ms. Biwi for her supports and also logistics behind scenes. And we are going to continue our communication and talking to each other, moving up to another level of engagement and collaboration. I really appreciate that. And Dr. Chai, thank you very much. And I'll see you next time.
Thank you, Professor Lu. I think we start talking about this seminar about 4 or 5 months back. Because of Prof. Lu, so personally I have a few chance to talk to a few professors from Purdue, and I think my school management, the university, is very keen to further develop the collaboration between the two sides. By the way, I teach different courses. One of the courses is virtual reality for manufacturing. And in my class, I think we have some European, Swedish university student. I hope to have one day have students from Purdue. Okay, and today 6 different speech. I think interesting in the sense of from different background, different applications. So I see the synergies. And for instance, our NTU teams, we are working very much on the underwater environment, from perception to point cloud reconstructions. And I see the application from the Purdue side is very much well developed. And our industry partner from Sweden, they are always very supportive to us in the sense of experiment, in the sense of data. So today is a very first time we have this chance to meet each other, to learn from each other. I hope we can have a second, a third kinds of collaborations. And indeed, the joint efforts for future research project, ground applications, many others, maybe industry projects, we can always connect through email, through WhatsApp. And I'm sure this new year, 2022, is a better year. Let's continue these efforts. I really appreciate all of you give this great support to the webinars. Thank you so much. Bye-bye.
Thank you.
Thank you, everybody.
Okay, bye.
Have a great weekend ahead.